Okay, I'm going to share the screen with you. And we have a lot of topics to cover. All right. Let's see. You tell me what you can see. This is the last slide we talked about. Am I right? Yes. This is the last slide I talked about.
Yes.
Okay. Yeah. So, and I asked you what is how the methane is a polar or non-polar, right? How many of you did it? How many of you did it? Is it polar or non-polar? Yes. Methane is a polar or non-polar? We're going to do a few things. So CH4. Yes. Is a polar molecule or non-polar? Yeah.
Non-polar.
Non-polar. Why is that?
Yeah, best lotion ever. It's $20.
So if you draw the Lewis dot structure,
no, smell it. Just put it on you. It
right?
smells like sweetness.
So you have like this.
Cold outside.
You have like this, right? And electronegativity of hydrogen is 2.1, carbon is 2.5.
Here, I'll bring it to you.
So 2.5 minus 2.1 is 0.4. So therefore, is non-polar. All those bonds are non-polar. Now this is a general statement. A molecule will be polar. Please write down. A molecule is a polar only when it has at least one polar bond. One polar bond. A molecule is a polar when it has at least one polar bond. I'll modify the statement after that, after giving some examples. So CH4 has all four CH, all bonds are non-polar. Therefore, molecule is a non-polar. How about this one? Who can tell me quickly? CH3, that's ethane. The first one is methane. Ethane. It's a non-polar or polar?
Non-polar.
Yes. And why is that? Because if you draw the first you have to draw the Lewis dot structure. Remember, right? That's basically our criteria. So you have to do the Lewis dot structure like this, and once you have it like this, and you put like this way, it's all Lewis dot structure, right? And you already know the hydrogen is 2.1, carbon is 2.5, all bonds are non-polar. Therefore, the whole molecule is non-polar. Is it okay? Following, right? How about this molecule?
Master,
Yes.
how did you get the 2.1 and the 2.5 again?
These are the electronegativity of those elements. Remember, I gave you the. Can you see this table? You see the table? Can you see the table?
No.
No. Let's try my application screen. Can you see the table now? Yes.
Yes.
So look at the carbon, group 4A, 2.5, hydrogen is 2.1, fluorine is 4.0 maximum, oxygen is 3.5, hydrogen is 3.0, and it goes like this way. These are all non-polar, these are non-metals, right? So I'm taking from there, and when I'll ask the question, if I do, I'll give you those numbers, okay? All right, so let's get going to our whiteboard, and we already took it there.
After that, did you say you just subtracted them?
Yes. So always to determine the polarity, you have to do ENA minus ENB, electronegativity of A minus electronegativity of B. So you have to calculate each and every bond in the molecule. All right, and then you see whether it has a polar bond or not. If it has at least one polar bond, molecule is non-polar or polar, sorry. And if it is no polar bond, then it's a non-polar molecule. Tell me this one, HCl, is a non-polar or polar?
You see Dennis now?
This is, remember, 2.1, hydrogen is 2.1, chlorine is 3.0. I already gave you the table if you have that in front of you. 3.0, and I go on from there. Come on. H2O is a polar, non-polar. H2S is a polar, non-polar. I'm waiting.
Would
H2O be a non-polar?
How about HCl? Let's start from the first one. HCl.
Oh,
Polar.
It's a polar. 3.0 minus 2.1 greater than 0.5 is a polar. That's right. It's a polar. All right? Because it has a polar bond. E is a polar bond. H2O.
Polar,
And why is that?
because
So you
of the Vesper model.
That is correct. You have H. Oh, you're going to Vesper model. That's pretty good. All right. So H, O, so O, and we have a like this one lone pair, and another lone pair. That's right. That's right. Yeah. So hydrogen is 2.1. Hydrogen is 2.1. And oxygen is 3.5. So therefore, 3.5 minus 2.1 is greater than 0.5. Is a polar. Yes or no? Everything okay, right? Yes? Water is a highly polar molecule. We'll talk about many things. Water has a lot of important properties. Any question about the water? How about H2S? How about H2S? The polar or non-polar? Remember, oxygen, sulfur also has a lone pair. Oxygen has a lone pair. Yes, is the polar or non-polar? Sulfur is 2.5. Sulfur is 2.5. Sulfur is 2.5. Electronegativity. Yeah?
Would it be polar?
Now let's see. H, S, 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 H. I went to three-dimensional structure, as you said. Lone pair and another lone pair like this way. Now tell me. So hydrogen is 2.1, and sulfur is 2.5. Sulfur is 2.5. Now tell me, is it polar or non-polar?
non-polar?
It's a non-polar. That is correct. That is correct. And you will see down the road, we'll talk about the once we apply this polarity, non-polarity of the molecular compound, then we'll go to the deep in the properties. One of the properties is solubility or the states of the matter, the liquid, solid, or gas. Please write down what are H2O is a liquid, as you know. H2S, same kind of molecule, group 6 is a gas. Very stinky gas, is very rotten egg smell, the hydrogen sulfide. But H2O is a liquid and H2S is a gas. Why is that? Because H2O is a polar molecule and it has so many other important properties we'll talk about down the road. H2S is non-polar and therefore it's a gas. Molecules are singly isolated from each other. NH3 is a polar or non-polar? Nitrogen is 3.0, hydrogen is 2.1. Polar or non-polar?
Non-polar?
Let's see.
It's polar.
Let's see. So we have a H. That's our three-dimensional structure first. The Vesper model. This, and lone pair. Now tell me, 2.1, they're all 2.1, right? They're all 2.1 and 2.1, and nitrogen is 3.0, 3.0. Yes? Now tell me, the polar or non-polar?
Polar.
The polar. That's right. So 3.30 minus 2.1 is 0.9. It's a polar. The polar. Very good. Let's do a few more molecules. You do this one. I'm going to write it up, and you do this one. CH3OH, methanol. CH3OH, methanol. So tell me what you have to do first. You have to first you draw the structure,
I'm sorry.
the Vesper model, or the three-dimensional structure, and then go on from there. You can draw the two-dimensional structure as well, but it's appropriate to draw the three-dimensional structure. That's for model. Methane, is it a polar or non-polar? Is it polar or non-polar?
Is it polar?
And why is that? How many does it have polar bond?
Because the OH bond is polar.
And does it have any other polar bond?
I don't think so.
Well, let's see. I'm going to do it here. Huh? So what is this on? Sorry. Let's say C, H, O, H. So that's the top of the screen, right? Right. And this is our H, right? That's a CH3 and OH. You have lone pair there and lone pair there. Now tell me. So carbon is 2.5, hydrogen is 2.1, you already know, and oxygen is 3.5, 2.1. So tell me. Are you going to change your answer? Probably.
Yeah, the CO bond, that's polar too.
Polar and polar. That is correct. So it is two polar bonds, and that means molecule is polar. Yeah, no problem. No doubt about it. That's right. Absolutely right. How about this molecule? CH3, O, and CH3. Yes, Makina? Yes, Makina Keys, what's up?
So if one of the bonds is nonpolar, then what would it make it? So if you have a polar and a nonpolar bond.
So it has a three non-polar bond, NP, NP, and NP. So it has three non-polar bonds. But remember, and two polar bonds. One carbon-oxygen one polar, oxygen-hydrogen one polar. So the criterion, a molecule to be polar, it must have at least one polar bond. This molecule has two. This molecule has two polar bonds, so it's okay, right?
Thank you.
Yeah, you're welcome. How about this one? Dimethyl ether. Dimethyl ether is a polar or non-polar? The polar or non-polar? Yes.
What are you eating?
Is it non-polar?
How many of you think it's non-polar and how many of you think it's polar? Remember, carbon is 2.5, oxygen is 3.5. They're all there right here, huh?
It'd actually be polar.
So one is polar, one's a non-polar. Anybody else? Polar is getting majority. All right, maybe let's see what happens. So CH3, draw the structure. So H, C is on the plane, O, and this is our hydrogen. We're in the three-dimensional structure, right? And H, so that's a CH3. Get a hit on. O, and then C, H, and let's put like this way. I'm going to put like this way. That's H, and this one is this side, H. So that's a CH3. Lone pair, there's a lone pair of oxygen, and carbon is 2.5. 2.5, oxygen is 3.5, and all hydrogens are 2.1, right? So all hydrogens are 2.1. So CH bond, polar or non-polar? Non-polar, right? Yes or no? Non-polar.
Yes.
Non-polar. non-polar. These are all non-polar. They're all of them, all three of them are non-polar. NP. Carbon-oxygen bond is a polar or non-polar?
Polar.
How about this oxygen-carbon bond, polar or non-polar?
Polar.
So therefore you have to change the A, right? Change your answer. Someone said non-polar, it's changing to polar. Is right? Yes or no? But you may be right. You can say right in the sense this molecule very typical. Although it is a polar molecule, it behaves like a non-polar because of the symmetrical structure. We'll talk about later. This is a little complicated. So we'll talk about the horn, we'll talk about the ethers. Ethers are usually behave like a non-polar, but it's a polar molecule. So you might be right in a different way, but according to our rules, we should say it's a non-polar. Everybody okay, right? All right. So that's basically enough drilling for some of the molecules, the polar, non-polar, and all those things. And by doing so, first thing first, as you know, that you have to draw the structure. Now I'm going to give you a series of molecules, and you tell me which is a polar, non-polar. All right? I'm going to give you a series of molecules. Molecule number 1, CH4. All right? CH4 is the methane, CH4. I'm replacing one hydrogen with a chlorine. So next one is CH3Cl. It's called methyl. CH3 is a methyl chloride. Next one, I'm going to replace two hydrogen from the methane. Is a dichloromethane. CH2Cl2. I'm replacing three hydrogen from the chlorine group. CHCl3. Does anyone know what is CHCl3? Have you seen it, or do you know the application of this? Anyone? It's a chloroform. Chloroform is used to as an anesthetic. It's a knocks people down. Long time ago, but it was not properly maintained, and therefore it has been stopped. Nowadays, there are some other anesthetic agents are available. It's a chloroform. Chloroforms. It is also known as trichloromethane. Last one is CCl4. Replace all hydrogen with the chlorine. Now tell me, which is, you know how to do that. And I'm going to wait for your answer. Which is the polar, non-polar, polar, non-polar. Please tell me. Shall I write this on first one? Polar or non-polar?
Non-polar.
NP. Thank you. Next one.
Polar.
Thank you. Everybody following, right? Whatever he's saying, I'm taking it, and it's true. It's right. That's right. Next one.
Polar.
Very good. Next one.
Polar.
Thank you. Next one.
Non-polar.
How do you know?
Because it's symmetrical and it evens out.
Wow. Wow, you took my answer from me. Wow. That is correct. CCl4 is non-polar. But according to the electronegativity model, it should be polar, right? It is a 4 polar bonds. Yes or no? Yes?
Yeah.
Yeah, but it is non-polar. So let's draw the structure of this one. You already know the structure of this one, tetrahedral. Let's draw this one as well. So we have a Cl, C, Cl, Cl, and Cl. If you do the mother molecule, the methane, also C, H, and Cl, H, the methane, CH4. So this is the non-polar molecule because the 4 hydrogens, this is 4 chlorine atoms are there. All the chlorine is 3.0, all chlorines are 3.0 and carbon is 2.5. According to the calculation, there is a 4 polar bond, but in reality, it is a non-polar. Why? Because it is a symmetrical molecule for different forces. So carbon to chlorine force, chlorine towards this way, so drawing the electron density towards chlorine, electron density towards chlorine, and electron density towards chlorine. So 4 equal forces acting upon carbon at an angle 109.5 degrees tetrahedral. It's a symmetrical molecule, therefore no residual charge on the carbon, and it is a non-polar molecule. So now remember our statement was the molecule is a polar when it has at least 1 polar bond. But look at this molecule has 4 polar bonds. So how come it is a non-polar? So you have to modify this statement. The statement is as follows. The molecule will be polar provided it must have at least 1 polar bond and its geometry, the three-dimensional structure permits the polarity. In this case, its geometry doesn't permit the polarity. In this CHCl3, you have a CH bond and CCl bond. It's asymmetrical. CH2Cl2 asymmetrical. CH3Cl asymmetrical, meaning not symmetrical. Therefore, they are all polar based on the polarity 3.0 to 2.5. But once you come to CCl4, it is non-polar. Now do the same thing. Very good point. Excellent point. Yes. Carbon
Professor?
Yes.
Can you say that statement one more time for me, please?
Sure. A molecule will be polar provided it must have at least 1 polar bond and its geometry, parenthesis 3D structure, and its geometry or three-dimensional structure permits the polarity. All right. So that's a modified statement about the molecule.
What was that last word?
So last word, this molecular geometry must permit,
She recognized
allow,
allow,
allow its polarity, allow its polarity. In this case, CCl4 doesn't allow the polarity because the symmetrical molecule, 4 equal forces pulling in the same direction, leaving carbon no residual charge, therefore no polarity. The bond angle is 109.5 degrees. How about carbon dioxide? Can someone tell me is it polar? Non-polar. Carbon dioxide. Is it polar? Non-polar.
Is it non-polar by chance?
How do you know? What is your
Didn't you say that? Yeah, didn't you say that earlier? Oxygen had 2 lone pairs.
yes? Yes, I'm right.
Yeah,
Yeah.
and
Yes.
yeah, that's as far as I got as that. But I remember you saying oxygen had 2 lone pairs, and the last time we used oxygen, it was non-polar, so that's where I got that from.
You're right, but your answer is not on the point.
Yeah, my answer's not complete. Yeah.
So let's say oxygen is 3.5, but yes, you tried. Let's say, don't take it like that. You take it positively. That's right. So let's say this oxygen is 3.5 and carbon is 2.5. So in principle, molecules should be polar. Yes or no? Yes?
Yeah, but isn't it non-polar because it's symmetrical?
That's the key word. That's a key word.
And
So that,
sorry.
yes.
Yeah. So oxygen, is it always going to be 3.15? Always?
Oxygen is always 3.5. Yeah, those are
Okay.
standard. Those are standard values. I have nothing to do. We have nothing to do. All in the periodic, all in the table. Yes.
Okay.
Yes. I'll give it to you when I ask the question. So you're absolutely right. It is according to the calculation. It has the 2 polar bonds, carbon oxygen. But because of the molecule is symmetrical, two opposite forces. One is pulling this direction, another is pulling this direction. So there is no residual charge or force operating on carbon. That's why this molecule is nonpolar. Remember,
So
yeah.
if it is symmetrical, does that mean that it will be nonpolar? Like if it is symmetrical, then
that is correct. If it is asymmetrical, then it's polar. Yes. Provided it must have a polar bond too. For example, the methane CH4, it is a symmetrical, but it is a 4 different bonds, but it is also a non-polar based on the calculation, 1 to 1 and 2.5. Yes, that's perfectly fine. Now let's.
Sorry,
Yeah?
I have one more question. I'm sorry. So like, if it was just CO, would it be polar because it would only have one?
If it is CO bond only with something else, it is a polar. That is correct.
Yes. Okay.
Because remember the methane CH3OH, you said is a polar because it is a polar. That's correct. Yeah.
All right. Thanks.
All right, very good. Let's go back to the screen sharing, and we'll go to the sum of the molecules, and we modified the statement based on our observations. And let's go on to this and see what we can get. And you tell me what you see from here, okay? All right. So let me put in the full screen, and let me use my pen. And so this one you already know, the table. Here you go. Carbon dioxide molecule has 2 polar bonds. Still, it's a non-polar molecule. And that's basically the question I will ask. Why? So the answer is, it has 2 polar molecules, 2 polar bonds, but its geometry is, its geometry is a symmetrical. The 2 opposite forces, one is pulling to this direction, one is pulling to the other direction. Does anyone know what this sign means? Let's see, I'm just showing, because it has some name, it is very important name. Does anyone know what the sign means? It's okay if you do not. It's called dipole moment. Dipole moment. D-I-P-O-L-E moment. M-O-M-E-N-T. M-O-M-E-N-T. Moment. Dipole moment. It's a physical term, but don't worry about it. So 2 opposite forces pulling in opposite directions. Delta negative, positive, delta negative. Although it seems to be polar, because of the symmetry nature of the molecule, therefore it is a non-polar. Very good. Now I'll give you some molecules. We already talked about it. Just I'm going to show it to you. For example, water molecule. As you know, the water molecule, delta negative, delta positive, and it is asymmetrical. Why asymmetrical? Because it is not drawn completely, because it has a 2 lone pairs, and they will occupy like this and like this. And because of that, the bond angle HOH bond angle is 104.5, not 109.5. If it is 109.5 perfect tetrahedral, then it could be non-polar. The answer is polar because the bond angle is less than 109.5, although it is tetrahedral molecule. Ammonia, NH3 is also tetrahedral molecule, but if the bond angle is 107.3, not 109.5, therefore it is not a perfect tetrahedral either. In other words, it's not a symmetrical. Since it is not a symmetrical, it is also polar molecules. Although it is a polar bonds, but its geometry also permits its polarity. As you can see, its geometry, and it is a polar. Likewise, if we take the CH2Cl2, we talked about dichloromethane, it is also 2 asymmetrical bonds, CCl bond. And these bonds are non-polar, these bonds are polar, but its geometry is such, it is not a perfect tetrahedral. Therefore, it is also polar molecules. Formaldehyde, it is a triangular planar. This bond is non-polar, NP. This bond is NP. The next one is NP, right? And this is the P, polar bond. And the force is drawing towards the oxygen, and it is the A. It is a triangular planar. You know the triangular planar, and therefore bonding is it's a planar molecules, and planar molecules, because of the planarity, the geometry is permitting to be polar. So the molecule is polar. Right, so these are some examples. We have many other examples also, and I'll ask you many different ways. The next one is a practice homework assignment. And whoever is here, only share this one. Please do not share with others. The friends could be your very close friends, but still he or she should be in the classroom. Okay, that's a requirement. That means you come and for the attendance, not like that. Therefore, it is only for all of you who are already here in the classroom. And I'm not going to put this one onto the blackboard. All right? So only you can have it and you work on it, and many of the questions will be asked from these points. So that's a practice homework assignments, and you read this one again and again in order to answer those questions that I will ask. And as you have seen in the past, whatever I tell, I ask. I do not no tricks, no nothing. What is the basic principle of the formation of molecular or covalent compounds, and how to name them, how to name molecular compounds. How do we draw the Lewis dot structure of molecular compounds? We talked about it in details, and you must know, right? Those will be in the test, no doubt about it. Why there are some exceptions to the octet rule in molecular compounds? Remember, sulfur, phosphorus, fluorine, etc. Right? All period 3 elements. They do show exception to the octet rule. In other words, they can be surrounded by more than 8 electrons, and 12, sometimes 14 electrons, right? And you know why it is so. PS2, 3p6, 8, it can have 3d empty orbitals, and that's why it is exception to the octet rule. Must read. Answer question will be asked from there. Question will also be asked, what is the Vesper model? How does it work? As you know, the Vesper model, we talked about it, right? 4 electron clouds surrounding the central atoms. And because of these electron clouds repel each other, negative charges, therefore they will try to stay away from each other as far as they can. And one such example is a tetrahedral molecule, X4 type. X4 type two-dimensional structure is 90 degrees. XAX, that is lesser than tetrahedral 109.5 degrees. Therefore, they will prefer to have 3-dimensional structure, and that is 109.5 degree angle, right? And that is due to the Vesper model. So remember that. How do we determine the molecular geometry of the molecular compound? We already talked about the special application of the Vesper model. What is the origin of polarity of the molecular compounds? Electronegativity difference. What is the electronegativity? It's the attraction of the electrons within a bond. When you have a molecule A and B, molecular compounds sharing a pair of electrons, depending upon the electronegativity or electron affinity of the atoms, individual atoms, someone will share more or less. The one which has a higher electronegativity will have a more, or those electron will share more electron density as compared to the other which is a less electronegativity. Therefore, you can determine the molecule, whether the molecule will be polar or non-polar based upon the absolute value of the difference of electronegativity of A minus electronegativity of B. If it is less than 0.5 non-polar, it is a 0.5 to 1.9 polar. Greater than 1.9, we are not going to talk about. Those are ionic compounds, which we already discussed a long time ago. Alright, so this is the origin of polarity of the molecule. What is the electronegativity? I just told you a few minutes ago. According to the Pauling scale, chlorine is taken as a 4.0 maximum. Based upon that, we standardize the values. Oxygen is 3.5, nitrogen is 3.0, etc., etc. What are the basic rules of molecular compounds to be polar? We already talked about it. Definition that you must have a one-polar bond, and its geometry must permit or allow the polarity. All right. Now let's go to the next step. States of the molecular compound. States of the molecular compound. So this is the one such the molecular compound. Many of them could be gas, could be liquid. Based upon the characteristics of the molecule is a polar or non-polar, that will determine the states of the matter, states of the molecular compound. You know the states of the matter. How many states of the matter do you know? Any matter has 3 different states, right? What are those states? Gas, liquid, and solids. Gas, liquids, and solids. Remember one of the questions I asked you earlier in this class? H2O is a liquid, H2S is a gas. Why? Why is that? You can determine, you can tell because of the polarity. H2O is a polar, H2S is a non-polar. But how do we apply that? That's basically what we'll do now. So states of the molecular compounds may exist in 3 different states: gases, liquids, and solids. There are some molecules, they skip one of the states. Some of them only have a gas to solid, and some of them has liquid to solid. They usually, very exception, very few of them. Very exception. Can someone give me one exception? All molecules usually have a gas, liquid, and solid. Yes? For example, it's H2O. H2O. Yes? Yeah?
Go for the one that with the exception of that carbon dioxide.
Yeah! Excellent point. Carbon dioxide has only gas and solid. That is absolutely right. Absolutely right. We call it carbon dioxide, so it's a dry. Carbon dioxide is also known as dry ice. Dry ice. For example, let's say you can have a water, right? H2O. H2O is, it will be converted to, let's say H2O is a liquid, for example, L for liquid, and it could be converted to steam, right? STM, or vapor, either way, right? Steam. And that's a gas. So gas, so H2O, once you heat it up,
That's a gas.
apply the
How
heat,
long is this class?
you can convert it to liquid, is converted to, basically, is converted to steam, the gas. And if you cool it down,
You're paying more attention than I am.
right, cool it, then you can get the ice.
Awkward.
So ice is our solid. Okay, right? So water could be 3 different states: liquid. You cool it down, put in a tray and put in a minus 20 degrees in your refrigerator. You can see the ice. Yes. So that's a solid. If you take the water and heat it up in a pan, you can get the gas. So 3 different states of the water molecule. But carbon dioxide, for example, the gentleman told me very nicely. So carbon dioxide, CO2 is always a gas. It's always a gas. All right. And it could be converted into only dry ice. Dry ice. Dry ice is the one basically they routinely use, right? Dry ice. Dry ice is routinely used when we make the movie theaters and all those things. Why? So dry ice, as you heat it up, basically it is converted to carbon dioxide gas, and it looks like a cloud. So when you make the artificial clouds in a movie scene, they basically use lots of dry ice. And it is a non-hazardous. Many people use liquid nitrogen, but it's expensive and it's to be hazardous too. So dry ice is so it goes to solid. Dry ice is a solid, yes, and it is in equilibrium with the gas, carbon dioxide gas. That is correct. You're absolutely right. Some of the molecules they skip the steps. Now, who can tell me what is the process called? Liquid is converted into steam.
You said she's not.
Tell me what is the process?
Oh God.
Someone tell me what's the process?
I've never seen either of you train your
Liquid water is converted to steam or gas, vapor. What is the process called?
Evaporation.
I haven't seen Megan train.
Yeah, vaporization.
No.
That is correct. That's right, vapor, vaporization. When water is converted to ice, what is it called? Yes? Yeah? Solidification, freezing, solidification, freezing. And you can convert the ice to liquid if you apply some heat. What is that process called? Tell me please. What is this process called? When solid is converted.
Sublimation. Sublimation.
It's not sublimation. Sublimation is coming to the other side. So when solid is converted to liquid, it's called melting. It's melting. Liquidification. Either way it goes. Melting. Now, when liquid water, when the steam is converted to liquid, what is that called? Steam, vapor, is converted to liquid, H2O. What is that process called?
Like, it just like seems like a bad idea.
Condensation.
What I think about.
Condensation. That is
literally
capsule, right?
going home about 2
Condensation.
more weeks after that.
Condensation. So solidification, condensation is gases to liquid.
I'm looking at it
Solidification,
as a full
liquids to
set.
gas.
Duh, I'll wear my
It is
fucking
also
mask.
for
I wear my
water.
mask while I
It's
do
called
class last night.
vaporization
I got a lot of
or
weird gloves,
freezing
but-
or melting when ice goes to water, and vaporization when it goes
But I'm
to
just
water
saying is
to
that we go
liquid
home,
water to
like-
steam. Someone told me sublimation.
So I'm like.
So what do you call
sitting
this
there.
one? Gas to solid. What is that called?
I have a cute little red sparkly mask.
No liquid state. That's
Sublimation?
That is called sublimation.
I'm
That is
truly buying
absolutely
it
right.
just because
That
I
is called
want to
sublimation.
take pictures.
Absolutely right.
That's the only
That
reason.
is called sublimation. Sublimation. Yes, gas could be converted to dry ice. It's called sublimation. SUBLIMITI, sublimation. MATION, right? Sublimation. Sublimation.
Girl.
Now, these are states of the matter, and changing
DoorDash
from
back
one
cool.
state to
I
another
remember one the
state,
other day.
and that depends upon few factors. Number one, temperature,
Yeah.
and the next one
We
is
should
the
have been
pressure.
friends prior.
Temperature is the temperature, as you probably
I've
know.
drank and- I've
Temperature
drank
is always
more than
expressed in
one
terms of
bottle.
the degree is Kelvin, and Kelvin equals to Kelvin scale. There are 3 different scale of temperature, right? One is called degree Celsius, and one is called degree Fahrenheit. That's what we usually use every day. And degree Celsius is metric scale. It's usually European countries, Asian countries use it. Then degree Fahrenheit is used in the United States mostly. And there's another scale called Kelvin. Kelvin is degree Celsius, whatever the degree, right? Degree Celsius. Degree Celsius plus 273. That's a standard value.
But at that point,
73 is the absolute temperature. When you take all those elements, all those molecules, gaseous molecules, and put in a minus 270 degrees Celsius, basically everything will freeze. This will cease to, not cease to exist, they exist, but they will freeze. No molecular motion, no nothing. So Kelvin is 0 degrees Celsius plus, degree Celsius plus 273. In other words, if you take 10 degrees Celsius, 10 plus 273, and that will be our 283 Kelvin K. Kelvin K. So there are, these are the temperature scale.
I mean, I eat my.
So the states of the matter, gas, liquid or solid, it depends upon 3 different states. Temperature,
Like, sometimes
2
before I
different
sit down, I
states.
just move the trash can closer.
Different conditions. Temperature and pressure. Temperature,
For
pressure.
what?
So now, when temperature decreases,
Like every other day.
as you see, yeah,
It just,
cooling,
it
the
happened.
temperature decreases or pressure increases. You can increase the pressure or
I've
both.
been trying to do it 2
The
or 3
forces
times a
of
week, so the
attraction
loads are smaller,
become
so I don't
important
have
to the
do, like,
point
2 or 3
that
loads in a
they
day.
cause
My laundry
condensation.
department.
So if you take the gas,
I told you.
cool it down, right? Basically, we're cooling down, right? Here we're cooling it down. The condensation. So steam is the vapor, 100 degrees Celsius, cooling it down, and you can increase the pressure as well. So when you increase the pressure and decrease the temperature, both the forces of attraction between the water molecules become very strong, and they start condensing into liquid. So gas molecules, which are moving freely, now they are restricted motion
This is especially
because it's a
hard with
liquid. It is a liquid.
Oh, yeah.
That's called condensation. Gas is liquid.
Transfer.
And then ultimately you can take this liquid and also cool it down.
She's like, I don't
If you
know.
go to more cooling, the pressure doesn't have much effect on the liquid. The temperature has tremendous effect. If you cool it down, ultimately it becomes solid. That's a solidification. So these states of matters depend upon
I actually
a
am
key
just a
force.
little-
That's called intermolecular
I don't know.
forces.
You're a little bit.
Intermolecular forces. How much time do I have?
Girl, how did you even get? Like, you
I
didn't
don't even
Oh, hello?
1 minute.
Did you drink a Ruby Water? Does anybody like the Ruby Beer
Sorry.
White Claw?
That's fine.
Because I don't like them. and
That's
I've
fine,
never
that's
had
fine.
one.
So these states also depends upon the intermolecular forces. There are 3 different types of intermolecular forces, and these are right here. So intermolecular forces, there are 3 different types. Their origin is electrostatic.
But like it's
That is
and, like,
attraction
when
between
you
positive and
don't
negative
like what someone else
dipoles.
is doing because you aren't there.
The strength of covalent bonds are also shown as for comparison. It's the strongest bond. Intermolecular forces are very weak forces. There are 3 different types. Please write it down. So intermolecular forces of attraction between molecules three different
She's
types.
good.
Yep.
London
It's
dispersion
just
force,
better than
you don't
like
have to
regular
remember
coffee
these
and
numbers,
everything.
but if you
Yeah.
do, great.
I
0.01
drink
to
this
2
like
kcals
I
per
have
mole,
in my room.
very
Like,
weak
I don't
force.
need to drink to like
Dipole
feel
dipole
better about
interactions,
life.
1.125
either.
kcals per
But
mole.
like, if I don't have
Hydrogen
a drink
bonding,
tonight, I'm gonna
2
lose
to
it.
10 kcals per mole.
I made the joke.
Why?
And covalent bonds are strongest
I don't know.
bond.
I have
Single,
another
double,
PowerPoint
triple,
tonight with some
they
of
can
my
vary
boys
from
over at
72,
So I
or
will be
it's not
presenting
200,
places
please
I've
change
had
it to
sex. I just need
72,
to add a couple places.
900 kcals per mole.
A lot of people
70.
1150.
Yeah, I know.
Bye.
All right, thanks for reminding me, okay? So intermolecular forces are three different types.
I do.
London dispersion